All right, so we just got a little introduction to rotational motion. Now we have to talk a little bit about when rotational motion concepts are applied, and then that'll get us more into some of the background concepts and addressing, finally getting towards the formulas. So we call the rotation of a rigid body as rotational motion. Now, a rigid body is a really simple demonstration. It's an object whose size and shape do not change as it moves. So something like a wheel, awesome, that's rigid. But when I think about that, like a wheel rotates, awesome, rotational motion. It's a great approximation for many real objects. Now, not every object does absolutely follow this. If you think about like a water balloon, for example, if I were to hurl a water balloon, even if I put some spin on it through the air, the mass distributes as it's flying and it constantly redistributes, and it doesn't necessarily maintain its original size and shape as it's going through the air. So a rigid body, rigid means that it has strong molecular bonds and the atoms we can model as individual particles and they maintain their shape as it moves. Okay, so it doesn't bend or elongate or anything like that. So there's three different types of motion that we when I get more than just a particle that I have to examine. One is translational motion, and that's really what we started. We also call it translational kinetic energy. So that's typically we've been doing particles as they go along a line, but as I start to examine more types of motion, I have to be more specific. So translational is just an object that moves in a straight line, and we can model it as a particle. Now, what this unit primarily deals in is rotational motion. And then we talked about that. We already defined it. It's an object rotates around a fixed axis right in the middle. So it rotates around in a circle, and it doesn't matter. It doesn't have to be a wheel. It can be something like this, which is like a stick, essentially, that's rotating around a fixed axis. And then we'll get into combination motion. And this object is rotating as it's following a projectile. So it's really both things going on. And then we have to discuss exactly how we do that, because we treat this as the translational point follows the regular projectile motion, but then it's also rotating as it goes through the air. And we talked about this with energy. This has rotational kinetic energy and linear or translational kinetic energy. And both things are going on at the same time. And it gets more complicated as we add more aspects to the motion. So this is a really stupid GIF. It's about an axe that flies through the air and just maintains its direct linear path without rotating. And it looks stupid because obviously it's not correct. And that's what's nice about physics, is the more we learn, the more we can examine things and the more accurate and correct we can be. So when I'm rotating a rigid body, there's an axle or some fixed point in the middle that everything's rotating about. And I've already introduced this concept, but every point, it doesn't matter if you're right here or right here, it has the same angular velocity. Angular velocity because this whole thing spins as one unit. So these 2 points have the same angular velocity. Now, if you're different distances from that, from the midpoint, right, you're going to undergo the same angular displacement then, but we talked about arc length as being S. You're going to have different arc lengths based on how far away you are. And we talked about this previously, and then we said that the velocity at any given point is the angular speed times the radius away. Every single point has the same angular speed. Different points have a different radius, so different points have a different velocity. So I got a quick check for you. Rashid and Sophia are riding a merry-go-round that's spinning. Sophia is twice as far from the axis. Her angular velocity, that is going to be the same as. They have the same angular velocity. Same question, Sophia's speed. Well, if she is twice as far, we said V equals omega R. If she's twice as far, Sophia is going to have twice the instantaneous velocity. Or her speed, for that matter, is going to be twice as great. All right, so here's another quick check. If you're taking a young child to Six Flags, and we've talked about this, and they're terrified of roller coasters, but they agree to finally go on the merry-go-round, where should you have them sit? Closest to the middle, because if you're closer to the middle, you undergo a smaller circle in the same amount of time, which means you have a lower speed. And of course, D is also a viable answer. So we've already covered uniform circular motion. But now I can have things that start at rest and start to speed up as they go and rotate. So the angular velocity is increasing. So when we had velocity increasing before, we said acceleration is our change in velocity over time. Well, now we have angular acceleration is our change in angular velocity over time. This is the Greek, it's not A, it's alpha. It's a Greek letter. It looks a lot like A. The way that I kind of do it is I give it a little hook up top. So mine's not as nice and neat, but it's easier to tell apart. Some people go as far as to kind of make it that fish, that infinity symbol, or the almost infinity symbol that we use for proportional to. But this is angular acceleration. It is slightly different than linear acceleration. A quick little note, I could have positive, and this gets back to the D word, positive and negative acceleration. And positive acceleration was speeding up in the positive direction, but it was also slowing down in a negative direction. And negative acceleration was slowing down in the positive direction or speeding up in the negative direction. Same concept with angular acceleration. Angular acceleration is positive when it's going counterclockwise and speeding up, but clockwise and slowing down is also positive. And it's negative if it's counterclockwise and slowing down or clockwise and speeding up. Because remember that clockwise is the negative direction and counterclockwise is the positive direction. And I talked about the right-hand rule for torque as a way to remember that. Lefty loosey, righty tighty, right? Okay, another quick check. Here we got the fan blade is slowing down. What are the signs of omega and alpha? So it's going clockwise. So omega is negative. It's going in the negative direction. However, it's slowing down in the negative direction, so alpha is positive. This is negative velocity, but it's slowing down. Same question. Now it's speeding up. So now omega is still negative, but if it's speeding up, alpha is also negative because it's speeding up in the negative direction. So we got a partner problem that we'll obviously take a look at in class, but it's taking a look at the concept of angular acceleration, which is our change in angular velocity over time. And we're looking at how many revolutions does it make? Well, that's actually our angular displacement. So we'll take a look at that too, and we'll do this example problem in class. So I keep going over this over and over again. This unit is nothing new. This unit is a review of motion, but instead of going in a straight line, we're talking about objects rotating. And I use the tire over and over again to help demonstrate this. And like I said, we take our variables and we put the word angular in front of it, okay? So before we had uniform motion, aka constant velocity, and non-uniform motion, aka constant acceleration. And now we'll have the same thing. And if we look at these formulas, and I put these in your outlines, if you look at the formulas are identical, except instead of position, it becomes angular position. Instead of velocity, it becomes angular velocity. And of course, instead of acceleration, it becomes angular acceleration. So nothing new. It's a great review of what we did already earlier in the year. Now, yesterday we talked about how velocity is the angular velocity times the radius away for your instantaneous velocity. Well, you can also have instantaneous acceleration, aka tangential acceleration. So this object right here up top is moving in a uniform circular motion. So the velocity doesn't change, so the acceleration is always directly towards the center of the circle. But now this object is speeding up as it goes around, so therefore the acceleration is getting larger and larger. And before we just said the acceleration was just v squared over r. Well, now acceleration, the magnitude of the velocity is changing, so the magnitude of the acceleration must also change. But the tangential component of that, so if you're the dot as you're riding around in the circle, you're getting faster and faster. The tangential component of the acceleration is alpha times r. not to be confused with the centripetal acceleration, which is still a equals v squared over r. It's super confusing, but there are technically two different types of acceleration going on. Centripetal acceleration from uniform circular motion, and a tangential acceleration as if you were the particle riding around the dot. It's very confusing. It can get very confusing very quickly. So we have to always make sure we're thinking clearly about whatever it is we're thinking about, which is, why physics is hard. But that's your quick little introduction into how we essentially solving rotational motion problems, similar to, of course, kinematics. So this is the rotational version of kinematics. And we'll talk more about then the rotational version of dynamics in the next section.